Question 3. Prove by induction that 1 plus a half plus a quarter plus ... plus 1 over 2 to the power of n equals 2 minus 1 over 2 to the power of n. So p of n is 1 plus a half plus a quarter plus ... plus 1 over 2 to the power of n equals 2 minus 1 over 2 to the power of n. So s is going to end up being 0. And where we get that from is the starting number s can be found by calculating the value of n, which makes the first and last terms on the left hand side the same. So the first term on the left hand side is 1, and the last term is 1 over 2 to the power of n. So we're going to swap that n for 0. So we've 1 over 2 to the power of 0. 2 to the power of 0 is 1, so this becomes 1. So we've 1 is equal to 1. So therefore, yes, s is equal to 0. So then p of 0, so we take the first term again, which is 1, and then we equal it to the right hand side this time. So 2 minus 1 over 2 to the power of n, but again we swap the n for 0. So s again is equal to 0, so that's our starting number. So then 1 over 2 to the power of 0, well 2 to the power of 0 is 1, so that's 1 over 1, or minus 1 over 1. So we have 1 equals minus 1 over 1, which is 1 equals 2 minus 1, which is 1 is equal to 1, which is true. So s is definitely 0. So next we assume that p of k is true, i.e. 1 plus a half plus a quarter plus ... plus 1 over 2 to the power k is equal to 2 minus 1 over 2 to the power k. So basically just wrote out the question again and swapped each of those n's for k's. So we assume that this is true, and next we prove that p of k plus 1 is true. So we basically write out what we already had above, but swapping each of those k's for k plus 1. So we have 1 plus a half plus a quarter plus ... plus 1 over 2 to the power k plus 1 is equal to 2 minus 1 over 2 to the power k plus 1. So next what we do is we take the left hand side, which is from 1 down as far as 1 over 2 to the power k plus 1, and we write it out again, but this time we include whatever term would have come just before the 1 over 2 to the power k plus 1. So this is our last term on the left hand side, so we want to also write in our second last term. So if the last term on the left hand side is 1 over 2 to the power k plus 1, then the second last term, the term that was just before that, must be 1 over 2 to the power k without the plus 1. So 1 over 2 to the power k is our second last term, so we write that in there. So we have everything else that was to the left of the last term, so 1 plus a half plus a quarter plus ... Then we have our second last term, and then we have plus our last term. So we also write down the last term. So 1 over 2 to the power of k plus 1. Then we group together the first few terms and the second last term. And hopefully this looks familiar to you when we group them together. We just have brackets around just to group them, that's all. So hopefully you can see that this is p of k. Well, the left hand side of p of k anyway. So it's 1 plus a half plus a quarter plus ... plus 1 over 2 to the power k. So that's what we have there in brackets. And we know from our assumption that this is equal to this, 2 minus 1 over 2 to the power k. So we just swap this for 2 minus 1 over 2 to the power k. So just this becomes this. We bring down the plus, and we bring down the last term, which was 1 over 2 to the power k plus 1. So this is where we are now. Now, remember, we want the left-hand side, so this is our left-hand side at the minute. We want it to equal the right-hand side, which is 2 minus 1 over 2 to the power of n. So, since we're trying to prove p of k plus 1, we actually want it to equal 2 minus 1 over 2 to the power k plus 1. So instead of an n, we want a k plus 1. So we have the 2, and we have the minus, but this somehow needs to become 1 over 2 to the power of n, which will actually be 1 over 2 to the power of k plus 1. So We're going to use algebra and we're going to use our laws of fractions and our laws of indices to rewrite what we have. So I'm just going to focus in on this for a second. So I'm going to cover up the bits that we don't have yet, just so it's not too confusing because there's a lot on the screen at the moment. Okay, so just to backtrack for a minute. We wanted to prove p of k plus 1. So we had 1 plus a half plus a quarter plus ... plus 1 over 2 to the power k plus 1 is equal to 2 minus 1 over 2 to the power k plus 1. So basically we just swapped each n for k plus 1, or you could say we swapped each k for k plus 1. So our left hand side, so this is everything on the left hand side of the equal sign. We wrote out again, but we also included the second last term. So we don't write out the right hand side. Okay, so we're going to ignore that for the moment. We want to end up with that at the end. So we've only got the left hand side, but we've also included the second last term. And I went through that a minute ago on how I got that. So just go back a couple of seconds on the video if you want to just recap where that came from. So now we have the second last term written into the left hand side. So this is our left hand side of our equal sign. Now from our assumption, which was up here in yellow, we know that we can replace this with this. So this was our assumption, p of k. We bring down the plus and we bring down the 1 over 2 to the power k plus 1. Now the next bit is where it can be a little bit tricky. So I'm actually going to cover up this section just so that we're focused in on what we need to. So we need this. So 2 minus 1 over 2 to the power k plus 1 over 2 to the power k plus 1. We need this to resemble this. Okay, so this is the right hand side of our original equation. Now instead of an n, we want k plus 1 because that's what we're trying to prove. So we have the 2 and we have the minus, but then we have two fractions, two algebraic fractions, and we only want 1. So we only want minus 1 over 2 to the power k. So we've got two algebraic fractions. So hopefully you can see that you need to come up with a common denominator. So we've got 2 to the power k as our denominator on the left and 2 to the power of k plus 1 as our denominator on the right. So if we can make these the same, because we know that we want our final answer, so our right hand side of our equation, not to be minus 1 over 2 to the power of n, but we want it to be minus 1 over 2 to the power of k plus 1. So we want to make this be a k plus 1 so that we can add or subtract our algebraic fractions and ultimately just have one algebraic fraction. So that's what we're aiming for. So you need to think to yourself, okay, how am I going to make this 2 to the power of k become 2 to the power of k plus 1 without changing the value of my fraction? So this is how we're going to do it. So we have 1 over 2 to the power k. So I'll just ignore the minus for the moment because we just want to sort out the algebraic part. So 1 over 2 to the power k. Well, remember with fractions, what you do to the top, you do to the bottom. What you do to the bottom, you do to the top. So if I multiply the top and the bottom by 2, I'm not changing the value of that fraction. 1 times 2 is 2. And 2 to the power of k times 2. Well, you could say, well, 4 to the power of k. But that won't help us here because remember, we want a common denominator. We want 2 to the power of k plus 1 on the bottom. So we're just going to write it as 2 to the power of k multiplied by 2 to the power 1. And then we're going to use our laws of indices that says multiplying pairs with the same base, we add the powers. So this becomes 2 to the power of k plus 1. So now we have 2 to the power of k plus 1 on the bottom, which is what we wanted. And our numerator is now 2. Because remember, what we do to the top, we do to the bottom. So we bring down the 2. Then we had a minus here and we didn't have a minus there. So if we want to factorize out that minus, we can take the minus from here outside the bracket, but then we need to also make this a minus, because if we're going backwards, minus times 2 over 2 to the power of k plus 1 is minus 1 over 2 to the power of k from here. And then minus times a minus gives a plus. So just be careful with the sign there. So 1 over 2 to the power of k becomes 2 over 2 to the power of k plus 1. So 1 over 2 to the power of k becomes 2 over 2 to the power of k plus 1. So this becomes this, and then we just brought the minus outside, and we had to apply a minus to this because otherwise it wouldn't be a common factor. So Now, hopefully you can see you have a common denominator. So 2 over 2 to the power of k plus 1 minus 1 over 2 to the power of k plus 1. Well, 2 minus 1 is 1. So we have 2 minus 1 over 2 to the power of k plus 1. And this is exactly what we wanted because this is now our right-hand side. So this was a proof by induction question that had a tricky bit of indices and algebra inside of it. So very good example. If something like this comes up and you are unsure of what to do, so this is the step here. So getting from this step to this step, that was the tricky bit. So hopefully you would have realized, well, I had two fractions here, two algebraic fractions, and ultimately I wanted one. So how do I make two fractions become one? Well, sometimes you could multiply them, you could add, you could subtract, you could divide. Any of those would work, but in this case specifically, we had to add them. And in order to add two algebraic fractions, you have to have a common denominator. And in order to get this to match with this, in order for these to be common denominators, the 2 to the power of k had to become 2 to the power of k plus 1. And any time you see your algebraic terms and your constants in your actual index notation, so you need to start thinking about your index laws or your indices laws. So this is where this came into it. And what usually comes up is the fact that you can change, you can manipulate algebraic fractions or normal fractions, so long as what you do to the top, you do to the bottom. So if you remember that rule, it's going to pop up somewhere in your index questions, in your indices questions. And it's very simple, something that you learn early on in maths. What you do to the top, you do to the bottom. So in this particular example, we multiply the top and the bottom by 2. But in other questions, you can multiply or divide the top and the bottom by all different terms, different numbers. But we ultimately needed to get to this. We needed 2 to the power of k plus 1. And in order to do that, we needed to multiply by 2 to the power of 1, which is really 2. But what we do to the top, we do to the bottom. And once we had our common denominators and we had factorised out, taken out our minus as a common factor, then all we had to do was subtract. And then we got where we wanted.